You survived this course. So again, the final is 2012 Wednesday from 4 to 6. The final practice exams are already online. Any exam that you took during the semester, any exam that is posted before is a practice exam. Okay? Everything is included, no exception, even the lecture today. The final info page, the information page, that means the equations that you will be given, information that you will be given in the first 2 pages of the exam. It's already online in the practice exam folder, so check it. Make sure that you know what is in there. Friday, which is this Friday, we're gonna, instead of a lecture, we're gonna have a help session at the same time at 8 a.m. in ISB 135. So send your questions by email. The easiest way is to tell me from practice exam, blah, 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 spring 2012, question number 12. So, and then we're gonna solve it. I'm gonna go over it in here. So I'll be waiting for your emails. The last email that I'm gonna look at is to add it to the slides because I have also to prepare yours. It's 4 p.m. Thursday. Now regarding OWL book or OWL assignment, guys, as I said in the class that I'm gonna extend the deadline. That implies if you did the homework before the new deadline, which is the 9th Sunday, the last day of the reading period, definitely you get the credits. So please stop sending emails about, oh, I did it before you extend the deadline. Does that mean I'm gonna lose a credit? Come on, guys, I'm helping you. Would I do that? I'm telling you that I'm opening all of these so that you boost your grade. Does that mean I'm gonna take credits if you did it before? Now, regarding the mastery one, if you have the mastery one, most of them, if you do 2 questions out of the mastery unit, it will give you a check, and that's all what you need. If the mastery told you, okay, you have a check, that means you're done from this. Because as if you do 2 questions right, that means you get the idea. You don't need to go through the 3rd question. Now, for the OWL book assignments, they are all optional. I put it all optional because I heard from most of you that, okay, it's more like a waste of time than me practicing. I prefer doing the mastery because they look more like the exam. They represent more what we're doing in class. This is why I put them optional. Now, then I get emails, oh, why optional? If you want it, if you particularly as a student in this class want me to put it required for you, send me an email. And I'm going to put it required for you particularly because you wanted that. The majority of the class wanted to do that. No, I'm not going to give them as extra credit if you do that because I already gave you extra credit somewhere else, which is the discussion board. Okay, so this is all what I'm gonna hear about OWL and assignment. Yes, I'm gonna do the 15% off. Yes, I said in the syllabus that I'm gonna drop the 15% of OWL. Yes, 15%. How I'm gonna calculate the 15%? So I open the OWL, see how many questions I asked you during the semester. Let's say I asked 600. Then 15% of that will be dropped. So if you didn't do 15% of that, you're good. You still get 60 over 60. Okay? So that's all about the OWL, the assignment, the extension. Yes, even the homework that was the 30th, due the 30th of November. Yes, its deadline is now the 9th. When I say I extended the deadline of all the homework, that includes all the homework, no exception. Okay? Now, after all of this, after all of these hundreds of emails about the OWL, what I was trying to do is helping you, just helping you to boost your grade. Okay, so now we're gonna get started with chapter 10. So whatever we cover in today's lecture from chapter 10 is included in the exam. What we don't cover is not gonna be included in the exam. One more question that I get by the email, how many questions is the final? The final is 36 questions. Okay, and definitely you have 2 hours for it. Okay, so let's get started with chapter 10. So the last time we did the iClicker for this one, Now I'm going to solve it. So we have the volume inside the pump is decreased. So I'm just going to put kind of, this is the pump. It has a volume of, a volume of 100 centimeter cube, centimeter, and then and it changed to 20 centimeter cube before the air flows into the tire. So that is connected to a tire. And then the air flow to the tire, the volume decreases. Suppose that the compression is isothermal, so T1 equal T2. Estimate the final pressure of the compressed air in the pump given an initial pressure, so the first pressure was 1 atmosphere. And definitely the number of moles during this process is not a change because clearly we didn't say that we lost some or we opened something and we lost. So, and N1 equal N2. We know that, and I'm going to insert in here, we know that the equation is P1 V1 equal nRT. This is the equation that we did, and this is equation number 2. This is for the initial state. Now the final state, which we're going to work with, is P2 V2 equal N2 R2, and this is equation 2. Now, if I divide 1 by 2, and I mean equation 1 by 2, not half or 1 over 2, that's going to end me up with P1 V1 over P2 V2 equal N1R T1 over N2R T2. But we just learned that T1 equal T2, so I'm going to cancel T1 and T2, they're going to cancel each other. N1 equal N2, R equal R. That implies that I'm ended up that P1 V1 over V2 equal P2. So all what I have to do is just to substitute the numbers. So pressure 1 is 1 atmosphere, volume 1 is 100 centimeter cube over 20 centimeter cube, which is V2. And I wouldn't convert anything because they are divided, so they're gonna cancel even if I change it. So if the pressure I substitute is in atmosphere, then P2 gonna be in atmosphere. If the pressure, the first pressure is in torr, the P2 gonna be in torr. So that would end me up to 5. So P2 equal 5 atmosphere, which is D. So this is how we handle if I have initial state, final state, state the first equation, the second equation, divide them by each other, see what's gonna cancel. It depends on the situation. In this situation, it told me that it's isothermal. That means at the same temperature, and I don't see anything claiming that the number of moles didn't change, so I can assume that. Okay, now in the coming question, which we're gonna do that, it's a different state, it's a different thing, but again, if it is a final and initial state, this is how we handle that. Okay? So let's go to the next eye clicker. stop it at 250. Okay, so I'll stop it while you check what you say. So I have the highest percentage is for D, 37%, but it's not a very high percentage. But D is the right answer. Okay, so again, the case in here, I have an oxygen tank. Definitely it's closed. That means the number of moles is not changing. At 6 a.m., when it is cold, the pressure equals 20 atmosphere. That's when the temperature is 20 Celsius. Now at 6 p.m., what would be the pressure? So we're looking for P2 if the temperature changed T2 equal to 6. Since it is a rigid oxygen tank, that means it's not going to collapse. It's not going to go, the volume wouldn't change. So V1 equal to V2. Clearly, the number of moles didn't change. There is nothing in the question that says, oh, the tank was open, we lost some moles of that oxygen. So again, what I'm going to do is P1 V1 equal N1 RT1, that's my first equation. P2 V2 equal N2 RT2, that's my second equation. Divide 1 by 2. That's gonna end me up with P1 V1 P2 V2 equal N1 R T1 over N2 R T2. I know the number of moles are the same, didn't change because N1 equal N2, V1 equal V2. So to get the second temperature, so T2 equal T1 P2 over P1. And definitely R gonna cancel out. Now all what I have to do is to just plug in the numbers. And sorry, we need the pressure. Sorry, I have to rearrange this because it's not asking about the temperature T2, it's asking about the pressure, so I did a mistake there. So I'm gonna rearrange it so that I'm getting P2. So P1 T2 over T1 equal to P2. So all what I'm doing is just rearranging this equation because this equation ends up to be P1 over P2 equal T1 over T2. So if I want P2, I'll take it up there, T1, T2 there. So P2 equal P1 times T1 over T2 over T1. Now, the only thing about PV and RT that the temperature always should be in Kelvin. It cannot be in Celsius. So you have to convert the temperature, which are in Celsius, to Kelvin to be able to do it. If we're talking about the pressure, it's okay to put it in another. You can put it in atmosphere, in torr, in bar, in Pascal, in kilopascal. But for the temperature in this equation, it must be in the Kelvin. So that's gonna be equal to the pressure. The first pressure is 20 atmosphere. Temperature is 20 plus 30 plus 273. So that's T2. T2 is 30 plus 273. 20 plus 273 to change it to Kelvin. Now both of them are in Kelvin, and the answer will be 21.4 atmosphere. Now we're gonna go to the next one. After everybody is done. Which of the following gas samples would have the largest volume if all the samples are at the same temperature? All of them, they have the same temperature, and same pressure. I'm going to stop it at 320.
I forgot the conversion from molecules to moles. Right.
Okay, so I'm going to stop it at 320 and check what you think. Okay. Stop it here and check what you think. And I have 63% for B. That's a very good percentage. B is the right answer. Okay? Now, so this question, it looks harder from what it is exactly. So the pressure PV equal nRT, okay? We want to calculate the volume, so it is nRT over P. The temperature is the same for all of them. The pressure is gonna be the same. R wouldn't change. So the only thing that is changing is N. So if the question is asking which one would have the largest volume, for the volume to be the largest, it's proportional to N. So the N should be the largest. So your next step is to calculate, to convert all these values, into moles, and figure out which one has the highest number of moles, and that implies this is the one that's going to have the largest volume. Okay? So I'm going to start with converting A from molecules to moles, which we learned in chapter 2, I guess, or chapter 2 or 3. 9 times 10 to the 23 molecules. For each 1 mole, we have Avogadro's number of molecules. So the calculation for that is 1.5 moles. Now in B I have mass. I need to convert mass into moles. So we know that the number of moles equals the mass over the molar mass. The mass is 8.01 gram. The molar mass of helium is 2.0 gram per mole. That ends me up with almost 4 moles. It should be 0.0. Okay? Now for C, it's already given to me in moles. I don't need to do much. Now I'm going to compare which one have the highest number of moles. B. B the highest number of moles. B the highest number of moles, which implies that the largest volume. Okay. And we're going to go to the next high clicker. I'm going to stop it at 3 minutes.
Intensity is mass over volume, right? It's like
Yeah, I converted Celsius to Kelvin, and then I used Bohr number for all.
Okay. So I'm going to stop right here and check what you think. And I have 45% for A, but it's not a very high percentage. A is the right answer. So first of all, clearly there is a relationship in here. They are giving you the density, the pressure, and the temperature, and they are asking you about the molar mass. So we talked about that there is a relationship between density and pressure and all of this, and we derived it before on Monday. I'm gonna do it one more time so that all of you can see it one more time. So, yay. So,
And I was like, I hadn't looked at my phone yet, and I was like, oh, it has to be like 8:30 by now. I was like, so
okay, and the computer. Where is it? Rosa.
I should just double click it on it more times.
So we can register and try to figure out what the fuck's
And then like
Okay.
tabs open. She's like, fuck. I broke it.
Okay.
gotten some of mine, but I don't know if I should get more.
Did you do anything? Basically, you can just do the negotiable, but I think I was trying. Yeah, that's the thing. Also, what is W?
Okay, sorry for that one.
Did you have to have like let W equal something?
Okay, so we know that PV equal nRT. Okay, we know that N equals the number of moles equal the mass over the molar mass. So I'm gonna substitute this in here. So PV equal M over the molar mass RT. Okay.
I mean,
Now I know that the density equal the mass over the volume. So if I put the volume down there, the molar mass up there equal M over V RT. So all what I did is rearrange the equation. Okay? So M over V, this one now is clearly the density. So P molar mass equal the density RT. Okay? I have the density, I have the temperature, I have definitely R, and the pressure is given. I need to calculate the molar mass. So the molar mass equals the density RT over P. Now the molar mass equals the density. Now all what I have after you get to that equation, the most important part is to make sure you're putting the pressure, temperature, all in the same unit, that the unit's gonna cancel. The density equals 0.480 gram per liter. The R that I'm gonna use depends on the pressure. In which unit is the pressure? The pressure is in torr, so definitely I have to use this one, this R value rather than the atmosphere, because the pressure is in torr. So it's 60 32.364 liter torr, Kelvin minus 1, mole minus 1. And definitely I have to put the temperature. And it must be in Kelvin because in here we have in Kelvin. So the temperature is 260 plus 273 over the pressure, which is 103 torr. Just I'm gonna. So I'm gonna rewrite this because it's messed up in here in this small space. So the molar mass equal density RT over P. The density 0.408 gram per liter times 62.364 liter torr, Kelvin minus 1, mole minus 1, multiplied by the temperature. I have to convert it to Kelvin by adding 273 to it, over, now this is in Kelvin, 103 torr. So the molar mass equal 155 grams per mole. Okay? So this is the relationship between the density and the molar mass. And usually this is a technique that we use to calculate the molar mass of gases is by figuring out its density, and from there, especially if it is an unknown, this is what we usually do in the labs. Okay, let's go to the next eye clicker. So the carbon dioxide generated by the personnel in artificial atmosphere of submarines and spacecraft must be removed from the air and the oxygen recovered. So in submarines, under the seas and everything, they generate CO2. This CO2 should be changed to oxygen down there, or in the space shuttles or any of those. So what they use is potassium superoxide, which reacts with CO2 to give this salt and 3 moles of oxygen. Okay? So submarines design team have investigated the use of potassium superoxide as an air purifier because this compound reacts with carbon dioxide and releases oxygen. Calculate the mass of potassium superoxide needed to react with 50 liters of carbon dioxide, 25 at 25 degrees and 1 atmosphere. So let's say the submarines, they already generated a 50 liters of CO2. At 25, the temperature is the room temperature and 1 atmosphere. How much superoxide they need, potassium superoxide they need inside that submarine to get rid of those CO2 that they generated?
What's the molar mass of potassium? What's the molar mass of
It's 39.
do this last time? That's just not
So I'm gonna stop it at 450.
Did I just set this really well? Oh, right. Whenever I do these, I always just blindly solve for something on that side of the equation.
Just start plugging in numbers and then they come out right. I could fall asleep right now.
Okay, so I'm gonna stop it at 450 and check what you think. And I have A for 38%, although it's a very low percentage, but A is the right answer. So this kind of equation is kind of a combination between chapter 10 and chapter 4, which is stoichiometry, because clearly you have a pressure and clearly you need to use the equation, the stoichiometry, to figure out how much potassium superoxide you need. So your first step is to figure out how many moles of carbon dioxide do you have there. So this is my first step. Gonna be PV and RT to figure out the number of moles of CO2. So the number of CO2 equals PV over RT. So N of CO2, the pressure that is stated is 1 atmosphere. The volume is 1 liter as given to us. Oh, sorry, 50 liters. 50 liters. Definitely, I'm gonna use the R. I'm gonna go just one slide back. Definitely, I'm gonna use this R because it has atmosphere, Kelvin, mole minus 1, which is the same as the pressure given to us. It's in atmosphere. If it is in torr, I would use the one in torr. If it is in Pascal, kilopascal, I would use that. So the R that I'm gonna use in here is 8.20547 times 10 to the minus 2. And I'm going to put the units there, liter, atmosphere, Kelvin minus 1, mole minus 1. And definitely the temperature, I'm going to change it to Kelvin, so 25 degrees plus 273. The N of CO2, in this case, the number of moles of CO2 ends up to be 2.04 moles. Okay? Now, this is not the end because I have to go back to the equation and see the stoichiometry. For each 2 moles of CO2, I need 4 moles of potassium superoxide. So mainly, I need double the amount. This is one way to think about it. For each 4 moles, you need 2 moles. So I need double the amount for potassium superoxide, or I'm going to do it the old way, which is going back to the equation, saying for 2.04 moles of CO2, for each 1 mole reaction, I have 2 moles of CO2. But for each this 1 mole reaction, I have 4 moles of potassium superoxide. So the N of potassium superoxide equal, this gonna cancel. Sorry, 1/4. So 2 times 2.04 moles This is the number of moles of potassium superoxide that we need. But the question is not asking about the number of moles, it's asking about the mass. So my next step, I have the number of moles, N equal the mass of potassium superoxide over the molar mass of superoxide. So the mass of superoxide equal N times the molar mass of superoxide. The molar mass of superoxide, potassium superoxide, is 71.1. So I'm going to do one more and save. So the mass of KO2 equal 2 times 2.04 moles multiplied by 71.1 gram per mole, which is the molar mass of potassium superoxide. The mass of potassium superoxide needed is 290 grams in this case. Okay? So this kind of question is a combination between the two chapters, chapter 10 and chapter 4. Okay. I'm going to go one that just in case somebody didn't manage to write that down. Okay. So now we're going to go to the next subject, which is talking about the molar volumes. So the molar volume, by definition, is the volume for 1 mole of a gas. And the volume of 1 mole of a gas, it doesn't matter what is that gas, at a standard ambient temperature and pressure, which we call the standard ambient temperature and pressure, those standard ambient temperature and pressure are 25 degrees, the temperature is 20 degrees Celsius, the pressure equal 1 bar. Under these conditions, which is room temperature conditions and pressure, because the pressure here is 1 bar, the temperature is 25 degrees, the volume for 1 mole of the gas equal to the volume of that box that is in this picture right here, which is equal to 24.79 liter per mole. This is the molar volume. So the molar volume is the volume for 1 mole of a gas at ambient temperature and pressure, 25 1 bar. So if now I tell you at step, what is the molar volume of any gas? That's going to end up being 24.79 liter per mole. And that can be used in questions that I ask you, what is the pressure of oxygen at step, at standard ambient temperature and pressure? And you know the volume, you know the molar volume, you know the temperature, you can calculate the pressure or otherwise questions, okay? So you need to know that the molar volume for most gases is the same. There is some exceptions, we're not gonna cover it in this course, but usually the molar volume for gases at those temperature and pressure is 24.79 liter per. Okay, so let's do an example in here. Actually, it's gonna win my friends to do things. So I'll go out and shop for my mom together. So I'm gonna stop it at 420. And this is gonna be our last slide. That means this is the last one that is included in the exam because we are out of time. So from slide 10 on for this lecture, they aren't included in the exam because on Friday we're gonna have it as a help session rather than keep going in the chat.
Okay, let's see
Where's the letter D?
Okay. Okay. So I'm gonna stop it right here and check what you think, guys. And I have 50% for A. A is the right answer. So first of all, okay, 1 minute. So first of all, we talked about the molar volume, and we talked that the molar volume for all gases at 25 degrees, 1 bar is a constant number. Now, what if we're talking about the molar volume at minus 20, which is lower than the 25 degrees? So by definition, the molar volume is the volume per 1 mole, so liter per 1 mole. In other words, it's going to be the volume that we have here, which is 2.5 times 10 to the 4 liters, over the number of moles, which is 1.2 times 10 to the 3 mole. So if you do the calculation, it's going to be 21 liters per mole. So this is the molar volume, Vm. We call it the molar volume, which is how much is the volume per mole. This is the molar volume of helium at minus 20. And I'll see you Friday. Send your questions if you have any.